Hey everyone, and welcome back to The Explainer. So, have you ever actually stopped to think about what's going on inside your computer when it comes to power? I mean, we all plug our devices into the wall, we watch that battery percentage drop, and we hear the fans spin up like a jet engine. But how do computers actually consume and, more importantly, save power at a microscopic hardware level? Well, that is exactly what we're going to explore today. We are looking at the absolute foundational principles of green computing.
But before we get into the heavy engineering, I've got a question for you to chew on. Picture a massive server sitting in a data center. It's plugged in, it's turned on, but at this exact moment, it's not processing a single user request. It is completely 100% idle. So, what is the real power cost of that idle computer? You'd probably think doing zero work means drawing zero power, right? Well, hold on to that thought because the physical reality of this hardware is going to totally shock you.
To figure this out, we're diving straight into some seriously rigorous source material, specifically a university lecture outline on green computing, CSE 407, Class 3. And what I absolutely love about this source is just how incredibly comprehensive it is. We are going to drill all the way down from high-level policy rules and market failures, straight into the microscopic physics of CPUs, and then right back up to operating system software. It's the whole shebang.
So here is our roadmap for the explainer today. We'll start with how policy dictates hardware, look at where the power actually goes, break down the math of CPU power, tackle this thing called the energy proportionality problem, and finally we'll look at managing power beyond just the CPU. All right, let's jump right into part one, from policy to hardware.
Now, you might be wondering, why do hardware engineers even care about this stuff in the first place? Well, the lecture points out a harsh reality. Voluntary action in the tech world just kinda doesn't work. We've got market failures like short-termism, companies being free riders, and completely ignoring environmental externalities. Basically, without strict rules, companies will almost always prioritize raw, blazing performance over energy efficiency. Because of that, we need frameworks. We have global ones like ISO 14001, Energy Star, the GHG protocol for carbon accounting, and WEEE for e-waste, but it gets highly localized too. The source specifically highlights frameworks like Bangladesh's e-waste rules of 2021 and the ESRI Data Act of 2012. And yeah, right now, some of these might be under-enforced, but trust me, they are tightening up. These are the mandatory rules of the game that engineers have to design within.
Let's put some real-world numbers to this so we can see the stakes. The syllabus gives us this great concrete homework scenario for calculating Scope 2 emissions, which are basically the indirect emissions from the electricity you buy. Let's do the math together. Step 1. Imagine a small office closet with just 10 servers, each drawing a base power of 500 watts. That's 5,000 watts, or 5 kilowatts of continuous power. Step 2. Let's say they run 12 hours a day. 5 kilowatts times 12 hours is 60 kilowatt hours every single day. Step 3. Multiply that across a 365-day year. You are looking at 21,900 kilowatt hours of electricity annually just for a tiny 10-server setup. When you multiply it over time, every single watt is absolutely crucial.
Which brings us to our second section. Where exactly does all that power go? The really important takeaway here is that power consumption is not just one big on-off switch for the whole computer. It is like a giant puzzle. Every single layer of the hardware and software stack is an active, hungry consumer of electrical power. At the absolute bottom, you've got billions of microscopic transistors physically switching on and off. Above that, the processors pushing the data around. Above that, your peripheral devices, storage drives, and memory banks. And sitting right at the very top, acting as the boss dictating how hard all this hardware actually works, is the operating system. If you want to build a genuinely green machine, you have to optimize every single rung of that ladder.
Okay, moving into section 3, the math of CPU power. This is where the engineering gets super interesting.
Let me introduce you to the engineer's ultimate secret weapon for controlling how much energy a processor eats. It's called DVFS, which stands for Dynamic Voltage and Frequency Scaling. See, back in the day, CPUs just ran at one fixed speed and one fixed voltage all the time. But modern processors, they are incredibly smart. They use DVFS to dynamically adjust their clock speed, that's the frequency, and the electrical pressure driving them, the voltage. And they scale both of these up and down on the fly, millisecond by millisecond, depending on exactly how much work needs to be done right then and there. To really grasp why DVFS is a total game changer, we have to look at the central formula for CPU dynamic power. Don't worry, it's pretty straightforward. Dynamic power, or P dynamic, equals C times V squared times F. Let's break that down. C is capacitance. That's essentially fixed by the physical design of the circuit board itself, so engineers can't easily change it on the fly. That means they have to manipulate the other two variables. F is the frequency, or the clock speed, literally how fast the chip is running. But the absolute most important variable here by a mile is V, the voltage. Notice that voltage is squared.
And that squared symbol right there, that is the massive mathematical aha moment of hardware design. Let's look at the difference. If you drop the frequency by 10%, you save roughly 10% on power. It's a strictly linear trade-off. But because voltage is squared in that formula, the dynamic completely changes. If you drop the voltage by 10%, you don't save 10%, you actually get nearly a 20% drop in power consumption. That exponential return is exactly why minimizing voltage is basically the holy grail of CPU power management.
So that covers how we manage the CPU while it's working. But what about when it's resting? Well, that brings us to the number 7. This represents the 7 specific CPU idle states defined by the ACPI standard.
These are known in the industry as C states, and they range from C0 all the way down to C6. Honestly, the best way to understand these is to think of them exactly like human sleep cycles. C0 is when you are fully awake, sitting at your desk, intensely focused on work. You are drawing maximum energy. C1 is like just closing your eyes for a quick second. You aren't actively working, but if someone calls your name, you snap back instantly. You save just a tiny bit of power. But as you move down to C2, C3, and so on, it's like falling into a deeper and deeper sleep. By the time you hit C6, the processor is in its absolute deepest hibernation. It's essentially shutting off major internal systems to save the maximum amount of power possible. But there's a trade-off, right? Just like you might need a strong cup of coffee to shake off a really deep nap, it takes the CPU a few milliseconds longer to wake up from C6 than it does from C1. So your operating system is constantly playing this incredible balancing act, trying to plunge the CPU into these deep sleep states the literal millisecond you stop moving your mouse.
All right, let's look at Section 4, the energy proportionality problem.
Remember that question I asked you at the very beginning of this explainer? What is the real power cost of an idle server? Well, here is the jaw-dropping answer straight from the lecture data. 50 to 70%. A typical enterprise server draws 50 to 70% of its absolute peak power even when it is almost entirely idle. So doing practically zero work is still costing you more than half of your maximum electricity budget. No way, right?
Let's look at this comparison to see why it's such a massive headache for data centers. In an ideal, perfect world, computing would be beautifully energy proportional, 0 watts at 0 load, scaling up perfectly evenly like a balanced scale. But reality is a lot harsher. A real server burns that 50 to 70% power budget even at a measly 1% load. Why? Because simply keeping the memory refreshed, keeping the networking cards listening for data, and keeping the motherboard powered up requires a massive baseline of electricity. This is exactly why server idleness is so massively, incredibly costly. Engineers have to fight tooth and nail to either turn idle machines completely off or pack them totally full of work so that 50% baseline penalty isn't just wasted.
And that leads us perfectly into our final section, managing power beyond CPUs. Because we have to look beyond the processor. One of the most striking examples of this comes from display technology, specifically OLED screens. Check out this table from the lecture. Because OLED screens individually illuminate every single microscopic pixel, rendering a completely black screen draws just the baseline power. The pixels are essentially turned completely off. But if you display a pure white screen, every single one of those tiny pixel LEDs has to fire at absolute maximum brightness. The result? That white screen draws 3 to 5 times more power than the black screen. This perfectly illustrates why switching your phone to dark mode isn't just about aesthetics. It is a literal device-level power management technique that measurably saves your battery.
So let's pull all this incredible info together. Based on the source material, here is the ultimate stack-wide toolkit engineers use to slash power usage. First, they apply dynamic voltage and frequency scaling for those sweet quadratic power savings. Second, they tune the OS to ruthlessly plunge the CPU into deep C0 through C6 sleep states during any idle time. Third, they manage peripherals by taking advantage of physics, like OLED color choices. Fourth, they aggressively power down idle storage and networking hardware. And lastly, they adjust software so it doesn't wake the hardware up when it doesn't need to. Basically, it is a complete top-to-bottom war on wasted watts.
Which leaves us with one final, kind of intense thought to end on. We've just spent this entire explainer looking at how incredibly hard engineers work using intense mathematics and physics just to minimize the electrical power going into these chips. But here's the thing. All that power that goes in eventually turns into heat. So if keeping the power down at the transistor level is this mathematically intense, what on earth does it take just to keep these massive servers from literally catching fire? Well, you'll have to stick around because cooling is exactly what's on the agenda for our next explainer. Thank you so much for joining me on this deep dive inside the machine. Catch you next time.